I think Shiva is the most excited student in this class. Hi Anjana, glad you have joined. Long time no see. Shiva is also, yeah, good evening Shiva, but why haven't you joined the class from last 3 days? We have just completed a chapter, you know. Is there any function going on in the GNV? Any kind of event? Because the attendance is very low. Uh, okay, because after that 4 to 5 days break, the attendance is very low. So I was thinking that something is problematic for you guys, like in my lecture or my strategy of teaching, the way of should I teach you. So I was working on myself, but here is the okay, okay. Hi Anjana, hi Suhana, how are you? Everybody is fine, na? So those who are not in the previous lecture, we are going to recall something that we have learned in the previous lecture. And a very funny thing for the previous lecture that there are only one student, but she is very attentive in that lecture and very responsive too. So I was not feeling bored in that lecture. Okay, I cannot say about the her end, but I have enjoyed that lecture. And that student was not, uh, uh, let's say, he is just the first in my class. So Harshili was that student, and thank you so much, Harshili, for being attentive. Okay, today you are. Today I hope the same from you. Okay, so guys, we have started with the fluid mechanics. Here's the lecture number 2 we are have. So yeah, you deserve it, Harshili. So we are here with our lecture number 2 on fluid mechanics. That is very important topic. Yeah. So from now onward, please be attentive because this chapter is very important and yet crucial. So there is lot in this chapter that you can take. Okay. So fluid mechanics is that the name of the chapter. We are on the lecture number 2. So the topic that we have to cover in NCRT, you will find the name as mechanical properties of fluid. Okay, just before we have covered mechanical properties of solid, and after that it is mechanical properties of fluid. Okay, but in your module it is written as only fluid mechanics. Okay, so the learning objective of this chapter, from this chapter, we would learn about the pressure inside a fluid and this pressure and buoyancy Archimedes principle. This will we discuss in fluid static, in which we deal when the fluid is at rest. Okay, statics, and that is the fluid kinematics, the equation of continuity and Bernoulli equation, and rest the other. Okay, so we have to cover the pressure inside a fluid that we have covered in the previous lecture, buoyancy and Archimedes principle, equation of continuity and Bernoulli's equation, viscosity and surface tension. So these are the topics that we have to cover in this chapter. Now, today, in the previous lecture, we have done with introduction to fluid and fluid pressure, Pascal's law and hydraulic machine. Today, we are going to see the variation of pressure with depth in a fluid as we move inside the fluid and go deeper and deeper. Then what is the effect on the pressure and how the pressure vary inside a liquid in with the depth? That is we are going to see. Then atmospheric pressure and gauge pressure. This is all we have to learn for today. Now we are going to recall So I will take a little extra time to recall so that Harshili, you will get it properly, and the other who have not joined the lecture in the previous class, so they will also get to know that what we have covered. Okay. So the very first question arises in your mind that what is a fluid? So fluid is a substance that have a tendency to flow. So a substance or element which can flow even under a small deformation or a small application of force. So you just slightly disturb the system and it will start flowing. Then that kind of substance is termed as fluid. So fluid has this tendency flow. ठीक है. So अब तक हमारे दिमाग में क्या रहा है कि व्हाट इज अ फ्लूइड. सो फ्लूइड को हम देखते हैं दैट इट इज अ लिक्विड टाइप ऑफ थिंग. ठीक है ना. लिक्विड इज फ्लूइड. नो, दिस इज नॉट द थिंग. A fluid is a substance which can flow. So who will satisfy this condition, that the tendency to flow with a small deformation or a small disturbance? Okay. I'm not saying it is small application of force. It will sound a little odd. The small disturbance, the small deformation that tend to flow. Okay. That makes the fluid to flow that much amount of disturbance or force. So if any substance is following that condition, it will lie in the category of fluid. So generally two types of fluid we have, liquid and gas, because gas also have a tendency to flow with a small disturbance. Got it? You can see the example of air with a very small value of changes of pressure, it will flow from one place to another place. Got it? So gas we can also take in fluid. Now, if I talk about pressure, so you will see in this video, we have a nail and a hammer. Okay. So what we have did, we just reverse the nail and now we are applying the force to it. So in which scenario it is easy for us to put this nail inside the wall? In this scenario. Okay. So why it is happening? It is happening because of pressure. Because pressure is nothing but, if you will see, pressure is nothing but it is defined as the normal force per unit area. Okay. See, if this is the area, cross-sectional area A, and we have applied a force perpendicular to the surface. Okay. So the quantity normal force per unit area is termed as pressure. Got it? So if this is the surface and a force vector is like in this direction, we applied a force at an angle theta. So we will resolve this force in two components. It is F sine theta and F cos theta. So this perpendicular component came into the picture of pressure. So if I write to pressure expression for this, so it will be F of sine theta divided by area. Got it? So always take that component of force which is perpendicular to the surface. Now, this quantity is a scalar quantity. I will discuss it later why it is a scalar quantity. And the unit of it will be Newton per meter square or Pascal. It is the same unit of stress. We have seen a stress now. The dimension of it will be m l raised to the power minus 1 t raised to the power minus 2. Now in this example, if you will see, this is a broccoli. So it is easy for us to cut the vegetable with the sharper end of the knife. And why it is so? Because the sharper end has a lesser area. Okay, sharper end, less area. Okay, and in the expression of pressure, you will see it is force upon area. If area will reduce, automatically pressure will increase. Okay, so it is easier for us to cut the vegetable with the sharper end instead of the blunt end. Okay, and that is why in that example of hammer and nail, it is easy for us to put the nail from the lesser area side to the wall so that it can penetrate easily in the wall, because at that point, suppose this is the nail, so this area is less than this area. So at this point, the pressure would be high, and this point, the pressure would be less. So we want a high pressure so that it can easily penetrate inside the wall. Got it? Now, you can also see the one of the example that sleepers under the railway track, we place the sleepers. These are the sleeper. Okay, you have seen it na in the very old railway track. These sleepers are made of wood, but nowadays it is made of concrete. You will see it. And why it is placed? It is placed because when the train will pass on this railway track, so there is a perpendicular component of force, which is the weight of that train, which would be, if you will see the area of this railway track, it is very less. So there is a chance of very high pressure development. Got it? And due to that high pressure, that railway track can broke. But due to this sleeper, which have a higher area than this, so all the mass or all the weight of the train will be supported by these sleepers. Okay, and these have a larger area than this railway track. So the pressure developed, which is higher in this case of only on the case of railway track, will be lowered when we place the sleepers. So that is why these railway track remains safe. Got it? The same question I have used. Why camel can easily walk in the desert, but we cannot? Obviously, it is a matter of pressure that we applied. This is our foot, a human foot, and this is the size of camel. Look at the size of it. So it is obviously greater than the size of a human foot. So area is large. If area is large, then pressure would be less. So if there is no sufficient amount of pressure, so it can easily, without so much of penetration, it can walk easily on the sand. But we have a lesser area, so there will be a high pressure, so we can penetrate more in the sand. That is why it is not easy for us to walk in the desert. Got it? Now, density I have discussed in the previous class. Density is nothing but mass per unit volume. How much mass you can confine in a specific volume, that ratio is termed as density. Okay, and it is the factor that is going to decide that which one of the liquid or material is heavier than the other. Okay, if the for example, honey and water, so which one is heavier? Honey is heavier because of the density difference. Okay, more dense is a liquid, more viscosity, more friction it will offer to you. Okay, it will very hard for us to move inside that liquid. Suppose that there is a swimming pool, two swimming pool. One of the swimming pool is filled with water, and one of the swimming pool is filled with this honey. So in which you can easily swim? You can obviously you can answer that water filled swimming pool. Why? Because honey is denser than water, so it will offer more friction when you have to apply more force to deep down inside it. Got it? So this is represented by rho, which is mass per unit volume. It is a scalar quantity. The unit of it will be kilogram per meter cube. and dimension of it will be ml cube. There is one more density you will get to know. It is the relative density. Relative density. Relative density is nothing but density of particular material, okay, divided by density of reference material. And that reference material is water in case of liquid, and gas in case of gas it is air. Obviously in case of solid it will be ice. Okay, so this relative density has no dimension because it is the ratio of density to density, so no dimension it have. Got it? And it is used to compare the density of two liquid. ठीक है ना? For example, the density of mercury is 13.6. Okay, and for example, this is just for example, the data cannot be true. So let's say not specifically mercury, for any particular material the density is let's say 2000 kilogram per meter cube. We know that density of water is 1000 kilogram per meter cube. So if I know the relative density of this material, it would be 2000 divided by 1000. So I know that relative density is 2, which is greater than 1. Okay. So this liquid, this particular material is heavier than water. Got it? If the ratio, note it down. Just a second. If relative density is greater than 1, you can say material is denser than water. Got it? And if relative density is less than 1, material is lighter than water. Or instead of lighter, you can say it rarer. Okay. So this information we are going to apply in the Archimedes principle, and based on that data, we are going to decide that which material can float inside a liquid, particular liquid, or let's say the liquid will be water. So which material has the ability to float inside the water, or which material will sink inside the water? So that relative density is going to told us. Okay. Now, so this is it. Example, this question. Try to solve this question, everybody. Try to solve this question. This is very easy question. Okay. So if the area of wall of a dam is 20 meters square and the normal force is 1500 Newton is applied by a water on it, then calculate the pressure applied by the water on the wall. So you need to calculate the pressure, okay, by the water. Pressure you have to find out. Area is given to us 20 meters square, and just a second, and the force applied here by the water is 1500 Newton. So try to calculate it. Everybody, try to calculate it. What is the pressure? This is for you guys. Okay. Just tell me the answer. Then we will move further. Suhana, Aisha, Arun Kumar, Shiva, Harshili. You have already solved it. Try to solve it again. Very good. Very good. 75. So pressure is nothing but force applied by area. Force is given to as 1500 Newton. Area is given to as 20. So it will be 75 Newton per meter square. Okay. Be careful with the units. So is the same for everybody. Shiva has already answered. Okay. Okay. So everybody got it? Any kind of doubt of anyone? The same thing it has been done here. Now, Pascal's law and hydraulic machine. So Pascal's law, we are going to generally going to see it. Pascal's law. So it is given by this French scientist Blaise Pascal's. Okay. So Pascal's law states that a change in pressure at any point in a confined incompressible fluid at rest is transmitted undiminished to all the point in the fluids, which means there is a fluid, okay, in a pot, and you have changed the pressure of that fluid from a particular end. So that change of pressure will go inside the fluid without any loss to the other end of the fluid. But the condition is that that fluid must be incompressible. You can see easily. Suppose, just a second. If this is the pot you have, you type pot you have, and there are liquid inside it. There is a liquid. Okay. And suppose here is a piston arrangement. Solid piston is here, so that you can move it back and forth inside the liquid. And this end is, let's say, open, and liquid is at this level. Okay. So what will happen if you push down this piston at this position? So this much liquid has been displaced from this position to here. So that change in pressure automatically will transfer to this end without any loss. Suppose this liquid is filled up to this point, okay, and this point is closed. This is closed. So what will happen if this fluid is compressible? So if you compress it, you are compressing it. If you compress it, so this amount of the liquid will be compressed. So there is a loss of pressure. The Pascal's law is not valid for this. That is why the Pascal has applied his brain and said that this law is valid for only incompressible fluid, because in that scenario only this change of pressure is going to undiminished, okay, without any loss. You can, in this example you can easily relate it. If this liquid is not compressible at all, so by any mean you are not going to compress it, no matter how much force you have applied. Okay. So that is the statement of Pascal's law. The change in pressure at any point in a confined incompressible fluid at rest is also necessary, is transmitted undiminished to all the point in the fluid. Okay. So this is the point where the pressure will be applied to this point and uniformly from all the direction. And pressure is nothing but the force perpendicular area. So these force line will be radially to this point mass. Okay. Now we are going to see it. This is the fluid element we have taken. Okay. Fluid element A, B, C, D, E, F. And we are going to see that on each phase, the variation of pressure is same. Okay. So we have three phases here, ADCF, ADCF. Try to note it down on this figure. ADCF, ADBE, and BECF. So these phases we have, and we are going to see the pressure variation for all the surfaces is same. Okay. How it is possible? Let's say for this, the screen is visible to you. Just a second. If I talk about this inclined surface, so there is a force acting perpendicularly to the surface by the liquid, and this is the pressure. Okay. So this force, let's say, is FB. This surface would be B. Now, this is the another surface. Got it? If this angle is theta, so this force has been applied because it is perpendicular to this. So obviously, it is also at an angle theta. Got it? So there it has two component. One of the component in this direction, in downward, vertically downward, which is F cos theta, and one of the component in the horizontal direction, which is F sine theta, and it is FB, so we can take it FB. Got it? Let's say this component is F C, and this component is F A. So you can say that FA, because this fluid, it is inside a fluid, and this fluid is at rest. So the net external force on the system must be zero, which means summation of all the forces will be zero. So if you equate these forces, force in the vertical direction, force in the horizontal direction. So in vertical direction, if you will see, this is the force which is acting downward, which is FB cos theta, and one of the forces acting upward, which is FA. So FA is equals to FB cos of theta. Question 1. This FC will equate this FB sin theta. FC FB sin theta. This is in horizontal direction. Equation number 2. Okay. Now we can say that if the area of this inclined surface is AB, so we can also resolve this AB into two component. One of the component is AB cos theta, and one of the component is AB sin theta. This area is nothing but the cos component of horizontal component of AB. So we can say that AB cos theta is nothing but AA. If the surface area of this surface will be AA and surface area of this surface will be AC, because force applied we have taken as C, FC. So area we have taken AC. AC is nothing but the vertical component of this inclined surface, which is AC AB, vertical component AB sine of theta. Now, if you calculate the pressure on this surface, so it will be pressure at C is equals to force at C divided by area of C. Force at C is nothing but FB sine theta divided by area at C is nothing but AB sine theta. AB sine theta. It will get cancelled. So it will become FB over AB. If you calculate for this horizontal surface, so P of A will be F of A divided by area of A. F of A also you put this value is FB cos theta divided by area of A is nothing but AB cos of theta. Cos theta will cancel out. So it will become FB over AB. And for the inclined surface, the pressure at B is nothing but FB over AB. So from these three conclusions, you can say that pressure at B is equals to, very good, FB over FA. What? What are you trying to say? Just a second. Hashira is saying that FB over FA. Regarding what? The pressure of B will be force at B, which is FB divided by area of B, which means area of this inclined surface. Okay. So you can see that PA is also equals to FB by AB, PC is also equals to FB by AB, and PB is also equals to FB by AB. So you can say that pressure at B is equals to pressure at A and pressure at C, which means that on a fluid element which is inside a liquid, a uniform pressure is acting in all the direction, and that is what the Pascal's law said. Okay, got it? So pressure inside a fluid, sorry, outside the fluid will be acting radially downward, and it is uniform in all the direction. Okay, and that is what it has been taught in this. Now, if you will see, this is a situation. The pressure at the bottom of the vessel, if vessel A, B, and C contains different amount of liquid, but height of the liquid is same in this way in each vessel. So what we have did, we have pour the liquid in these three vessels, maintain the same level of liquid. Okay. So what do you think? What if I take this line? So this point, and this point. You can see above it, there is different amount of liquid. It's also different, and it is also different. But if you will calculate the pressure at these points for C, for A, and for B at the same height, let the height is h, sorry, depth is h for three of the point, you will find that pressure is same, PC, PB, and PA. And that is what we have seen in the previous example. For inclined surface, it is also same. For vertical surface, it is also same. And for the horizontal surface, it is also same. And why it is coming? Because at the same level, the liquid, the pressure will be same. Okay. So they are at the same level. So the pressure at these points will be same, irrespective of the amount of liquid filled inside there as well. Okay. Now you can say that ki in that fluid element, these are not at the same level. But I can tell you this fluid element, for your understanding, I have made it bigger. But this fluid element is very, very small in size. Okay. So that is why you can say that they are at the same level. Now, hydraulic machine is the one of the most important uh, application of Pascal's law. Okay. So these are the some most common hydraulic machine you have seen. These are the hydraulic brakes. These are also known as disc brake. Okay. I hope all you have seen it, everybody of you, because nowadays it is very common thing to be seen. It is also nowadays they are coming in the bicycles also. Anna, you have seen it in a motorbike. So these are the disc brake, also termed as hydraulic brakes. Hydraulic jack or lift. Yeah, this is, I think, I hope that you have seen it. Okay. And this is the hydraulic press. Now, what are the principle on which they are working? So here we have filled an incompressible fluid. Okay. So what we have did, we are going to apply the Pascal's law. This is the piston here. Okay. We have applied a pressure on it, or we have compressed it. So in result of that, we have changed the pressure of this side. Okay. We have compressing it. So the pressure would be changed. So this change of pressure will travel to this side without any loss, because Pascal's law says that. So it will apply the same change of pressure on this area. Okay. So this will come up because it is going down. So this will come up. So that is why with this small arrangement, very small piston, we are able to lift this heavy kind of object. Okay. And that is the very important application or very useful application of Pascal's law. Okay. Hydraulic lift is also the one of the most desirable industrial used machine. Okay. Whereas a small force input, you will get a very large force output. Okay. So these are the area A1. This is the area A2. We apply our original force. F1 is equals to P1 into A1. Where it is come? Let's say the P1 is equals to F1 upon A1, force upon area. So F1 is nothing but P1 into A1. Pascal's law says that Pascal's law says that, suppose this is the hydraulic lift we have taken. Okay. Applied a force F1. Here we get a force F2. Okay. By this application of this force, we have changed the pressure by delta P. Okay. Let's say the initial pressure was the atmospheric pressure. So we have taken it atmospheric. And now the pressure is P1. So change of pressure delta P is nothing but P1 minus P atmospheric. Initially, this end is also on atmospheric pressure. Only the atmosphere is applying the pressure on it. Okay. But when this pressure change come, it will go this side without any loss. That is the Pascal's law. So delta P is same for all of them. Let's say the final pressure of it will be P2. Initial was P atmospheric. So delta P for this side will be P2 minus P atmospheric. But according to Pascal's law क्या कहता है कि this change in pressure of one side will go to the other side. Same. So delta P1 is equals to delta P2. Put the value P1 minus P atmospheric is equals to P2 minus P atmospheric. This will cancel out. So we can say that P1 is equals to P2. P2 here, we can also write it as force upon area. So force we will get as P2 into A2. And suppose this area we have taken A2 is 10 times of the area of A1. So put the value. F2 we have, because you can put P2 as P1 because both of them are same. And you will put the value of P1, which is nothing but F1 into A1. So it will be F1 A1 into A2. You put this 10 times of A1. Okay. Sorry, it is F1 upon A1. So this A1 will cancel out. So you will see that F2, the output force that you will have, is 10 times larger than the input force. And by reducing this area more, you can get this time. You can increase this. Okay. If you increase this 100 times of this area, the force you will get as output is 100 times greater than the input force. Got it? So that is a very beautiful application or very useful application of Pascal's law. I hope everyone is clear with this. Huh? Any response from you? Any kind of doubt with the Pascal's law? Everybody, I'm asking you. Shiva, Suhana, Aisha, and yeah, Harshili, Hashira. Do you get it? Shiva has responded. Thank you so much. Okay. Yeah, put the thumbs up. If you get it now, just give the reaction as thumbs up. I will understand that you have get it. Okay. Don't need to write it. Now. Okay. So Shiva, try to solve this question. Why hydrostatic pressure is scalar quantity even though pressure is for force divided by area? है So the answer is this. Because hydrostatic pressure is applied everywhere in every direction. Is the There is not a particular direction for this pressure. So that is why we have not taken it as a vector quantity. And one of more reason is that it is not follow the vectors law of addition, subtraction, multiplication. So that is why we cannot consider it to be a vector. Got it? Now, this is a question for you. In a hydraulic system, a piston with an area of 21 centimeters squared. Pay attention. It is given in centimeter square. Pushes on a liquid with a force of 38 Newton. The far end of the hydraulic pipe connected to a second piston with the area of 100 centimeters square. Now, what is the force on the second piston? It's a very easy question. So try to solve it. Okay. Now, what is given in this question? A1, the smaller area, is 21 centimeter square. So firstly, we will convert it into meter square. So 21 into 10 raised to the power minus 4 meter square. A2 will nothing but 100 centimeter square. So it is 100 into 10 raised to the power minus 4 meter square. Because 1 centimeter square is equals to 10 raised to the power minus 4 meter square. Got it? And force that is applied on this area, F1, is given you as 38 Newton. So what we are going to do? We are going to find out the pressure applied on this area. P1 here is nothing but F1 over A1. F1 is given to you as 38. Area is given to you as 21 into 10 raised to the power minus 4. So it will be 38 into 10 raised to the power 4 divided by 21. The same area will be on the other side. Sorry, the same pressure will be on the other side by Pascal's law. Pascal's law says that P1 is equals to P2. So P1 is equals to P2. You can write it as F2 by A2. F2 is equals to P1 into A2. P1 you have already calculated, Newton per meter square. It is 38 times 10 raised to the power 4 divided by 21 into A2 is 100 cent. 100 into 10 raised to the power minus 4. This plus 4 cancel with this minus 4. So it is nothing but 3800 divided by 21. This is the value of 4. So you can do the calculation further. Newton. Okay. So it is obviously greater than 38. The initial force. Got it? So it is 1.81 10 raised to the power 2 Newton. Now variation of pressure with depth inside the fluid. As we move deeper inside a liquid or a fluid, what is the variation of pressure? It is very important concept. So try to be attentive. So this liquid has a density rho, and we have considered again a fluid element inside the liquid or fluid. The height of this cylinder, the elemental cylinder that we have considered, fluid element, is H. And let's say this surface has a area A, the same area, surface area will be of this side. The point is 1 here and this point is 2. The weight supported by this fluid element is mg. Okay. Let's say the force acting on this surface is F1 and it is downward direction. And in this side, this fluid want to come inside. This fluid want to come inside this fluid element. And this is a hypothetical fluid element. We have not inserted something inside it. This is just the assumption. So this fluid is applying a pressure in this direction, in the upward direction. Okay, so there must be a force which is upward in upward direction. Now at equilibrium, what we can say, because how we can apply the equilibrium, because this element is in rest. So F external, according to the Newton's law, it will be 0. Because at rest there is no acceleration. F is equals to ma. If a is 0, then F external will be 0, which means sum of the forces will be 0. If you talk about this, at this surface, only F1 is acting and mg is acting downward. So these forces are balanced by this F2 because there is no other force acting on it. So this F2, which is in upward direction, will be equals to this F1 plus mg because they are both in downward direction. So F1 plus mg is equals to F2. Simple. Now you should take the difference of it. F2 minus F1, we have take this on the LHS, RHS side. F2 minus F1 is equals to mg. Now you can write F2 as P2 into A2 and F1 as P1 into A1. So put the value, you will have P2 minus P1 into A2 and A1, but A2 and A1 here are same as A. So we can take it out as common. So P2 minus P1 into A is equals to mg. Now, we know that mass is nothing but density multiplied by volume, because in the definition of density, what we have seen, density is the ratio of mass per unit volume. So mass here is density into volume. Okay. We'll put this in the expression this. And volume, you can say, for this cylinder, it is area into height. Okay. Height of the cylinder is given to you as h, and area you can consider it to be A. Okay. Put this value of mass, which is rho into area into h, in this expression. So what you will get? You will get as P2 minus P1 into A is equals to rho A H into G. This area and area will get cancelled out. So the expression that you will have it, P2 minus P1 is equals to rho G H or rho H G. So you can see here, if I take this elemental cylinder to the top of this vessel, okay. So this top have no liquid supported by it. Only the atmospheric pressure is acting on it. Only the atmosphere is outside, that is applying a pressure. So only the atmospheric pressure is outside the liquid. Okay. So if you consider this P1, which is the pressure at this surface one, if you take this as P ATM, so P2 is nothing but P atmospheric plus rho H G. So you can see that the pressure is linearly varying with depth. The linear relation. Got it? So this is a very important expression. So in static fluid pressure at same vertical height is same throughout the fluid. Okay. If you take this point, this line on which this surface 2 is lying, and take any number of point, so all of the point have the same pressure as P2, and which is P atmospheric plus rho H G or rho G H. Okay. Now, so for this, you can answer this question: why the blood pressure in human is greater at the feet than at the brain? Why? Because easily you can see at your feet the depth or the height has been increased, you know. So at your feet the pressure would be more because it is P atmospheric plus your height into density plus gravitation. So the extra rho hg factor will come, and that is why the pressure at your feet is greater than the pressure at your, okay. Got it? Now you can easily answer to this paradox. They are at the same level, so no matter what is the shape of the container, if they are at same level, the pressure would be same. Okay. Now atmospheric pressure and gauge pressure. Atmospheric pressure, because we know that, yeah, very good, Shiva. These are equals. Atmospheric pressure is, we know that we are surrounded by a sheet or a blanket of the air, you know, around the earth, which is termed as the atmosphere. And what do we have in the atmosphere? In atmosphere, we have gases, and these gases are attracted by the gravity. You know? That is why we have an atmosphere. So these gases constantly applying the pressure on the surface of Earth, and that pressure is termed as the atmospheric pressure. So the pressure of atmosphere at any point is equal to the weight of column of air of unit cross-sectional area extending from the top of to the point, sorry, from that point to the top of the atmosphere. In simple word, you can say that the pressure exerted by the atmospheric gases surrounded by us, okay, in the surrounding of us, the pressure exerted by the atmospheric gases is the atmospheric pressure. Okay. So if this is a column that we have, and inside it there are the gas, which is air. This is the earth surface. So if you take this much of height, this much of the air will exerting the pressure on it. The amount of air is this. If you take at this B, so only this much amount of the molecule executing the pressure on it. Okay. But if you see at the sea level, the value of the atmospheric pressure is 1.013 10 raised to the power 5 Pascal. So it is represented by its own unit, which is ATM. So 1 ATM is nothing but 1.013 10 raised to the power 5 Pascal or Newton per meter square, which is a good value of pressure. Okay. In this example also you can see this is the bottle. We have covered it with a, let's say, a thick paper and press it, and then we tilt it. And after some time, if you left your hand, the water will not go outside. This will hold it. And why it is so? Can you guess it? It is due to the air pressure, because air is constantly applying the pressure to it, and this pressure is greater than the pressure applied by the liquid inside it. But what if you take the needle and put it inside the bottle multiple times? So what will happen? This will the water will go down. Why? Because when you doing this, you will allow the air to get inside, and it will exert the pressure outside inside the liquid also. Okay, so the downward pressure is for air plus water, and upward pressure is only for air. Okay. Now, barometer. This is the last topic that we are going to cover. Okay. So barometer is a device that we use to that helps us to measure the pressure difference. Okay. So this is developed by the Italian scientist Evangelista Torrisoli. Okay. So it is used to measure the atmospheric pressure. So this is the setup of it. We have a vessel which is full of mercury, and this column, this glass tube is also filled with mercury. So what will happen? We will, okay. So what will happen? We put this glass tube inside this. Okay. So the mercury, this is inside the this vessel. So we will see that mercury somehow will go down, and at certain height it will stop. So here this is the vacuum, because there is no chance that air would come inside, because all the open point is inside the mercury also. And you will see the height that it would have cover is 760 millimeter. Okay. So we can say that only in the condition of atmospheric pressure, the value of uh, inside this glass tube, the height that mercury column will cover is 760 mm. So we will discuss it in the later on classes with much more detail. Okay. Till now, if you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive. Thank you so much. Okay. Take care of yourself. If you have any kind of doubt, you can ask. Okay, guys. Thank you so much.